There is one winter in modern American memory that still feels like a ghost story. A month when the cold did not just sting your cheeks, but reached into every corner of the map and refused to leave. Meteorologists still bring that year up in quiet conversations, the way pilots talk about one terrible flight that changed all the rules. Now, the same structures in the atmosphere that shaped that ghost year are flickering back into view. Forecast models that should disagree about the details are whispering the same outline. People are already throwing around phrases like systemic atmospheric collapse. So tonight, instead of chasing headlines, we are going to see whether the air above us is quietly setting up something far more serious than a normal storm. Back in 1985, the United States experienced a cold wave so intense that it became the benchmark for almost everything that came after. It was not just one brutal morning where the news showed frost on oranges and reporters throwing boiling water into the air. It was week after week where the atmosphere seemed locked into a pattern that refused to change. Records fell across entire regions, pipes burst, rivers choked with ice, and cities that thought they knew cold suddenly realised they had underestimated what Arctic air can do when it has a clear highway south. Forecasters today still reach back to that winter when they want to test whether a new event is truly historic. They pull up old charts and animations from 1985 and layer them mentally over current maps. They ask themselves whether the jet stream is bending in the same way, whether the core of the cold is diving into the same corridors, whether the timing of each push looks familiar. When an analog match is weak, they move on and call the new pattern something else. When an analog match is strong, they start to worry. Right now, those analogs are stronger than most of us would like to hear. Long-range forecasters began to notice it first. They saw the hints that a major Arctic outbreak could strike in January, and they quietly circled the middle of the month on their calendars. At that point, everything was still fuzzy. You cannot say with confidence 3 weeks out which town will drop below zero, or where the freezing line will sit on a specific day. But you can see the broad strokes. You can see whether the atmosphere is setting up to be gentle, average, or something that might be talked about for decades. The closer we move toward the present, the sharper that picture becomes. Medium-range models start to show individual storms. High-resolution runs start to paint where ice, snow, and heavy rain are likely to fall. Usually, as you close in on an event, the different forecast models begin to agree. They drift toward a shared solution, with only minor differences around the edges. That is called convergence. It is comforting. It means the atmosphere is behaving in a somewhat normal way, and our tools are reading it clearly. What is happening now is more unnerving. The models are converging on the existence of severe cold, but they are fracturing on how it expresses itself. In one run, the deepest cold pours into the northern plains and then slides east to the mid-Atlantic. In another, it dives more directly into the central and southern states. A third keeps the harshest anomalies over the interior west, while still flooding the east with air that is far below normal. The exact geography changes, but the core idea does not. The atmosphere wants to send a vast pool of brutally cold air south, and it wants to do it more than once. That is where the phrase systemic atmospheric collapse begins to creep into the conversation. It sounds like something out of a disaster movie. People imagine the sky itself failing, as if the air above us might suddenly vanish or fall. That is not what forecasters mean. When they talk about the system collapsing, they are describing something more subtle and, in some ways, more disturbing. They mean that the usual checks and balances that keep the jet stream wobbling around some average position have broken down. Instead of oscillating gently, the whole pattern tips hard in one direction and then gets stuck there. To understand why that matters, it helps to picture the atmosphere as a fluid engine rather than a static blanket. Think of heating a pot of water on a stove. The average temperature of the water might be warm, but what you feel on your skin depends on whether you are dipping your hand into the still surface or into one of the churning hot plumes that rise from the bottom. Weather is those plumes and swirls. Energy in the climate system is redistributed through storms, cold fronts, and heat waves. When that redistribution becomes lopsided for long enough, you do not just get a bad day, you get a regime. In 1985, the regime was clear. A deep trough in the jet stream carved itself over North America and invited Arctic air to flood into the continent again and again. Every time the cold retreated a little, it seemed to reload and surge south with renewed strength. The pattern was not simply cold, it was reloading cold. That is why the memory of that winter still haunts people who study the atmosphere for a living. It was a demonstration that the system can sustain extremes far longer than most of us are comfortable imagining. Today, the analogue is not perfect, but it is close enough to demand serious attention. We are seeing the jet stream bow southward in a way that opens the door for polar air to reach much farther into the lower 48 states than usual. We are seeing blocking patterns over the Pacific and the Atlantic that act like walls, keeping that trough from sliding away. It is as if the continent has become a bowl, and the coldest air available is about to be poured in, not once, but in several rounds, each separated by just enough time for people to start hoping it is over. This is where the difference between a storm and a pattern becomes critical. A storm is the visible tip of the iceberg. It is the snow on your driveway, the ice on the power lines, the rain hammering your roof. A pattern is the shape of the jet stream that allows those storms to form and line up like beads on a string. You can shovel a driveway, you cannot shovel a jet stream. If the underlying pattern favours repeated surges of cold and repeated collisions between that cold and moist air from warmer regions, then impacts stack on top of each other. Meteorologists are watching that pattern emerge in the data right now. They see the signatures in upper air charts that show strong high-pressure ridges where they do not usually sit, feeding energy into deep troughs over the continent. They see signs of the polar vortex higher in the atmosphere stretching and wobbling in ways that often precede severe cold outbreaks. In plain language, the cage that usually keeps the harshest Arctic air locked near the pole is bending. It has not fully shattered, but pieces of that cold reservoir are already leaking south. There is another piece to this that makes people uneasy. The cold air that is on the move is not normal winter chill. It is air that is many degrees below what would be expected for this time of year. That difference between what is happening and what is typical is called the anomaly. It is why a temperature that looks modest on paper can still have serious consequences. If your region is used to mild winters and you suddenly experience temperatures 10 or 20 degrees below the local norm for days on end, your infrastructure and habits are not designed for it. Pipes freeze, power demand surges, roads become dangerous in ways drivers have little practice handling. So when forecasters talk about a pattern that resembles 1985, they are not promising that every number on the thermometer will match. They are saying that the structure of the atmosphere looks like it is preparing to deliver vintage cold across a huge area. Vintage here does not mean charming, it means old-fashioned in the worst sense. The kind of deep cold that used to be part of a rarer background climate, now reappearing in a world whose systems and expectations have shifted. As this pattern locks in, individual storms become almost secondary. You may hear arguments online about which model run is right, or whether the cold will peak on one day or another, or whether your specific city will see a particular mix of snow, sleet, or freezing rain. Those details matter for local planning, but they can also distract from the bigger picture. The bigger picture is that the atmosphere is aligning its pieces in a way that strongly favours repeated winter hits and prolonged stress, even if any one short-term forecast still has some uncertainty. This is also why some people react with suspicion when phrases like systemic collapse start trending. They see the gaps between different forecasts and assume someone must be hiding the truth. In reality, the gaps themselves are part of the story. Our models are very good, but they are still approximations of a fantastically complex fluid system wrapped around a spinning planet. When the system is behaving in an unusual way, the models will argue with each other around the edges while still agreeing on the main threat. The disagreement does not mean nothing is happening. It means something big is happening in a way we have limited historical examples for. In the middle of all this, there is a human temptation to tune out. If you have lived through endless headlines about polar vortex events, bomb cyclones, and once-in-a-generation storms that seem to arrive every few years, it is natural to feel numb. It is easy to believe that every alarm is just another attempt to grab attention. That is why the analogue to 1985 is so important. It forces us to anchor our thinking in a real, documented period when the atmosphere did something extraordinary. It reminds us that there is a difference between hype and a pattern that has already proven what it can do. You and I do not need to become experts in jet stream dynamics to grasp the stakes. We only need to understand that weather is not random chaos. It is shaped by large-scale structures that can sometimes fall into configurations that strongly favour certain outcomes. Right now, the configuration over North America is tilting steadily toward a mode where repeated waves of Arctic air are favoured, and where those waves can reach farther south and east than most winters allow. That is not a guarantee of catastrophe. It is a warning that the dice being rolled for each new storm are loaded toward extremes. And yet, for all of this focus on cold and patterns in the upper air, we have barely touched the ingredient that often turns a harsh winter into a genuine disaster. Cold air on its own can be survivable if the lights stay on, the roads are clear enough for help to move, and the snow can be ploughed and pushed aside. The real nightmare begins when that cold pattern meets a fire hose of moisture from distant oceans. The fire hose in this case is an atmospheric river. That phrase sounds poetic, but it describes something very real, and it can be tracked in numbers and satellite images. Imagine a band of air a few hundred kilometers wide and thousands of kilometers long, loaded with water vapor pulled from the tropics. It is invisible to your eyes, but on special satellite maps, it glows as a ribbon of deep colour, a vein of humidity that can feed storm after storm. Under normal circumstances, these rivers of moisture are part of the way the planet balances its books. Warm oceans evaporate water into the air. That vapour holds heat, and atmospheric circulation carries it toward higher latitudes. When the vapour condenses into clouds and rain, it releases that stored energy. It is a global transport system, shifting heat and water from the equator toward the poles, like a conveyor belt that never stops. The trouble begins when that conveyor belt lines up with a stalled pattern of cold air. The river keeps flowing, while the gate ahead stays locked in place. Instead of one storm tapping into that moisture and then moving on, you get multiple waves forming along the same corridor, each one drawing from the same deep source. From the ground, it feels like the sky has forgotten how to turn off. Right now, that seems to be what the atmosphere is threatening to do. One moisture feed appears to be coming from near Hawaii, where warm ocean water and steady trade winds evaporate and then funnel vapour into the mid-latitude jet stream. Another feed may be rising from the Gulf of Mexico, a region that often supplies storms with humidity in cooler months. When those two streams of vapour merge into a single river and then collide with entrenched Arctic air, you have the blueprint for remarkable ice and snow. If you pull up a map of integrated water vapour, which is a way of measuring how much moisture is stacked through the depth of the atmosphere, you would see something that looks like a finger stretching from the subtropical Pacific toward the heart of the continent. On its own, that finger does not guarantee disaster. If it passes over mild air, you get heavy rain, maybe flooding. If it passes over a region with temperatures just below freezing at the surface, and a deeper cold layer aloft, it drops snow. But in this case, the vertical temperature structure is far more treacherous. Think of the atmosphere as a layered cake. Near the ground, you might have air that is below freezing, dense, and stuck in place by terrain and high pressure. Above that, perhaps a kilometre or two up, the air can be several degrees warmer, even nudging above freezing, because it has been pulled from a more temperate region by the jet stream. Higher still, the air turns cold again. That warm slice, sandwiched between two cold layers, is the breeder of freezing rain. Here is how the process plays out, one invisible step at a time. Snowflakes form high in the cloud where temperatures are well below freezing. As they fall, they pass through the warm layer aloft and melt into raindrops. Those drops then continue downward into the shallow cold air near the surface. They become supercooled, meaning they are still liquid even though their temperature has dropped below the freezing point. The moment they touch a surface, they flash into ice. From your window, it might look like ordinary rain. On the ground, it is something different. Every railing, tree branch, roadway, and power line quietly collects a growing shell of glassy ice. It does not pile up in drifts the way snow does. It clings, it adds weight. 1/4 of an inch of glaze on a network of branches and wires can translate into thousands of extra pounds tugging downward. A 1/2 inch or more can snap limbs, topple poles, and collapse structures that have stood for decades. What makes this kind of event so cruel is that it does not require the air temperature to be dramatically low. Many people are mentally prepared to be careful when the thermometer shows something like 10 degrees below freezing. They understand that everything is dangerous then. Freezing rain, however, can occur with readings just below freezing in that shallow surface layer. People step outside, feel air that is merely chilly, and underestimate the risk. Vehicles that were fine 1 hour can become uncontrollable the next, as a transparent film spreads over every exposed surface. The role of the atmospheric river is to keep that process going much longer than usual. In a simple winter storm, the moisture feed is limited. The low pressure centre moves, the cold and warm fronts sweep through, and the conveyor belt breaks. With a strong river of vapour anchored to a persistent jet stream configuration, new waves of low pressure can spin up along the same corridor. Each wave can drag a fresh burst of warm air over the shallow, cold dome, renewing the freezing rain threat in cycles. Forecasters can see this reloading effect in their models. They watch one storm slide through, then another spin up on its trailing boundary, drawing on that same deep plume of vapour from the Pacific or the Gulf. They see how the track of each wave lines up with the temperature structure at the surface. A small north or south shift in that track can determine whether a specific city sees plain rain, heavy snow, or the worst mix of ice. That is why forecast maps often show sharp gradients over short distances in events like this. When you hear them talk about the freezing line, they are not describing a single clean border. The atmosphere rarely offers such neat geometry. Instead, there is a zone where the balance can tip back and forth as the low-level cold air thickens or thins, as the warm layer above deepens or shrinks. Within that zone, an extra degree or two at a given level can flip the outcome. One town may wake up crusted in ice, while another, just a short drive away, has mostly snow that ploughs can handle. The frustrating part for both forecasters and the public is that these differences can evolve quickly. As each wave taps the atmospheric river, it can drag its own patch of warmth inland, nibbling away at the cold air near the ground. At the same time, fresh Arctic air masses may be sliding south behind the storm, trying to refill that cold reservoir. The result is a constantly shifting battleground where small timing differences can mean a lot. Yet even amid those local details, the larger story remains the same. The river keeps feeding, the pattern keeps favouring, and the risk of repeated icing persists. There is another reason these events are often worse than they first appear on model output. Numerical weather prediction systems are built on equations that describe how air moves, cools, warms, and carries moisture. They have improved dramatically over the past few decades, but when it comes to narrow filaments of intense moisture, especially those that reach deep into the tropics, models can underestimate just how much water vapour is actually available. When that underestimated vapour slams into very cold air, the resulting precipitation totals can surprise even experienced meteorologists. We have seen this happen before with classic atmospheric river events on the west coast. Forecasts call for significant rain. Reality delivers staggering amounts that overwhelm rivers and hillsides. In an ice storm set up east of the Rockies, the same underestimation can manifest as thicker glaze than expected, heavier accretion on lines and trees, and a much broader swathe of crippling conditions. Those are the kinds of surprises that turn a bad night into a regional emergency. Think about what happens in a town that has just endured a major ice storm while locked in a pattern like the one we are describing. Power crews work around the clock to restore electricity. Tree branches still hang precariously over roads. The ground is covered in a frozen shell that makes every step calculative. As soon as the grid limps back to life, another wave forms along the atmospheric river and aims for the same region. The cold at the surface has barely had time to relax. The shallow freezing layer is still there. The next round of supercooled rain arrives. This is when the concept of a reloading cyclone becomes more than a technical phrase. Each new low-pressure system that rides the jet stream corridor taps the same moisture supply and interacts with the same stubborn cold dome. To residents, it can feel like one storm with brief pauses, not separate events. The physical damage accumulates, so does the psychological stress of living in a landscape where everything feels brittle, from tree limbs to social routines. There is a cruel asymmetry here. It is relatively easy to recover from a heavy snow if temperatures remain cold but stable afterward. Plows clear roads, the snowpack compacts and becomes manageable. With ice, removal is slower and more laborious. Roads can be salted and sanded, but sidewalks, steps and driveways often stay treacherous. When that ice is bonded to power infrastructure, the only solution is to physically remove or repair what has broken under the strain. Now add the reality that in many of the most vulnerable regions, infrastructure was not built with frequent severe ice storms in mind. Poles may be older, lines may be routed through densely forested corridors. Redundancy in the grid may be limited. In places where snow is relatively rare, even a modest freezing rain event can push systems to the edge in a pattern that lines up repeated atmospheric river pulses with repeated cold surges. That edge can be crossed again and again in a single season. For people on the ground, forecasts that mention atmospheric rivers and freezing rain profiles can sound abstract compared to the simple question they care about. Will it be safe to drive? Will the power stay on? Can schools open? These local decisions depend on how well we translate those abstract patterns into clear, grounded expectations. That is one reason we are walking through the mechanics together. When you hear that a strong moisture plume is converging with entrenched cold air, you can now picture what that means, not just for dramatic weather maps, but for the tree outside your window and the lines on your street. It is also why it helps to keep track of the bigger repetition, not just the next named storm. If you hear that another wave is forming along the same corridor a few days after the first, and that the cold at the surface has not fully scoured out, that is a signal. It tells you that the system above is still in a mode that supports reloading. It tells you that even if a brief thaw arrives, the stage may already be set for the next act. We have focused so far on the moisture engine and the shallow cold near the ground, but the question lurking underneath is why this particular pattern is so eager to keep reloading. An atmospheric river does not decide to park over a continent by itself.
It is guided by stronger, deeper currents in the atmosphere. Currents that originate far to the north in a band of frigid air that circles the pole like a crown. To understand why the freezer door is open long enough for multiple waves to tap that moisture, we have to climb into those higher flows. The answer lies in the structure of the polar vortex and how it can stretch, contort, and even break into several pieces, each one capable of sending vintage cold south into the path of that relentless river. High above the storms we see on weather maps, there is a different kind of river of air circling the planet. Meteorologists call it the polar vortex, and in its simplest form it is a band of strong winds in the stratosphere that races around the Arctic.
When that band is tight and fast, it acts like a fence that keeps the coldest air bottled up near the pole. When it weakens, stretches, or breaks into pieces, that fence fails. The cold inside can spill south in ways that feel sudden to us on the ground, even though the story began far above weeks earlier. In recent years, the term polar vortex has been used loosely in headlines and conversations. People talk about it as if it were a specific storm or a monster that descends over a city for a few days. The reality is both less dramatic in shape and more dramatic in consequence. The vortex itself never drops down as a solid object. What we experience instead are the side effects when its structure changes and allows Arctic air to escape its usual cage. Under normal winter conditions, the vortex is fairly symmetric. The winds circle the pole like a well-behaved racetrack, and temperature gradients between the Arctic and mid-latitudes stay strong but orderly. The jet stream, which lies lower down in the atmosphere, responds by flowing in a relatively smooth band with only gentle waves. Cold fronts still sweep through, storms still form, but the extremes are moderated by the stability of that larger ring of wind above. Things change when sudden stratospheric warming events occur. In these episodes, the air high above the Arctic can warm by tens of degrees over just a few days, while the ground below remains bitterly cold. That warmth does not come from the surface. It is driven by powerful waves that propagate upward from lower latitudes, disturb the flow aloft, and dump energy into the stratosphere. As that happens, the tight circulation of the vortex weakens and the once smooth racetrack begins to buckle. As the vortex weakens, The winds that used to race from west to east slow down and can even reverse direction. The once circular shape stretches like putty being pulled by invisible hands. In some years, that stretching simply displaces the core of the vortex off the pole, parking the main cold pool over one side of the Arctic. In more extreme cases, the stretching continues until the vortex fractures into two or more distinct lobes, each one a self-contained reservoir of deeply cold air. If you picture the vortex as a spinning top on a table, this is the moment when the top begins to wobble violently and then splits into fragments that roll in different directions. Each fragment can set up shop over a different continent. One can anchor over North America, another over Eurasia. From the surface, you see this as a powerful shift in the pattern of cold outbreaks. Instead of one region taking a quick hit and then recovering, several regions can be exposed to repeated doses of vintage Arctic air. Not every sudden stratospheric warming event leads to extreme winter weather in the same place. Sometimes the main impacts show up in Europe, other times in Asia or North America. Sometimes the vortex recovers quickly and the surface pattern relaxes. The point is not that every disturbance aloft is a disaster. The point is that when we see signs of a fractured vortex and a jet stream bowing south over the same region again and again, the probability of persistent cold rises sharply. Right now, the pattern that troubles forecasters is one where lobes of the polar vortex appear to be favouring North America. Charts of atmospheric height and wind at high altitudes show a stretched circulation, with cold pools displaced away from the pole and aligned with the continent. That provides a pipeline for Arctic air to flood southward in waves rather than trickles. Each wave is not just cold in an everyday sense, it is cold compared to what the local climate expects for that time of year. This is where the idea of a temperature anomaly becomes crucial. An anomaly is simply the difference between the observed temperature and the long-term average. If a town normally sits at 40 degrees Fahrenheit in midwinter and suddenly drops to zero, that is a 40-degree negative anomaly, even though zero might be routine somewhere else. The human and infrastructural impact depends on that difference as much as on the raw number on the thermometer. Maps of anomalies during major vortex disruptions often look surreal. Vast swathes of land are painted in shades that correspond to 20, 30, or even 40 degrees below normal over huge areas. That does not always mean that every place has reached absolute records. It means that the entire climate deck in that region has been shifted downward in a way that stresses everything built for a milder baseline. Homes, roads, water systems, and even ecosystems are temporarily asked to operate in a different climate zone. Think about a city that usually sees light freezes and occasional snow, but rarely spends entire days below the freezing mark. When a vortex fragment parks overhead, that city can experience a stretch where daytime highs stay below freezing and nighttime lows plunge far lower than usual. Materials that never quite froze in ordinary winters now contract and crack. Reservoirs that usually remain liquid or only skim with ice can lock up more deeply. The sense of strangeness people feel in their bones comes in part from this mismatch between expectation and reality. Forecasters sometimes describe such cold as vintage. They are comparing the pattern not only to specific years like 1985, but also to an older climate regime when deep winter cold was more common. In a warming world, that phrase sounds like a contradiction. How can we talk about intense cold in a planet that is, on average, heating up? The answer lies in understanding that warming changes patterns and extremes, not just the mean. It can load the dice for both unusual heat and unusual cold, depending on how the atmosphere redistributes its energy. When snow covers a broad region and skies clear under high pressure, the ground loses heat rapidly at night. The snow acts like a bright mirror that reflects sunlight during the day and a blanket that traps cold near the surface at night. If that snowpack sits over flat land in the interior of a continent, particularly in parts of Canada and the northern United States, it becomes a breeding ground for intense cold pools. These are the air masses that can reach -30 or -40 degrees Fahrenheit in remote areas, even as people far to the south are still thinking about chilly rain. Now connect that with the fractured vortex above. The lobes of cold air in the stratosphere help guide where surface high-pressure systems and cold air masses form and move. Once a cold pool develops over snow-covered terrain, It tends to deepen under clear skies night after night. Then, as the jet stream sends a new trough dipping south, that reservoir can be tapped again and again. Each time a front sweeps across the border into the lower 48 states, it drags down air that has been aging and intensifying over that frozen landscape. This is the reloading effect meteorologists worry about. After one Arctic blast moves through, you might expect the atmosphere to gradually moderate, allowing a slow return to seasonal norms. In a regime where cold pools are regenerating quickly and the vortex remains distorted, that moderation does not fully happen. The lull between blasts shortens, and the starting point of each new cold wave is lower than before. It is as if the freezer door never quite closes, so every opening chills the room faster. From a human perspective, this changes the rhythm of winter. Instead of one clearly defined extreme event followed by a gentle thaw and a sense of closure, you get a sequence of hits. Heating systems run near capacity for longer stretches. Energy demand spikes put sustained pressure on power grids and fuel supply networks. Minor damage from the first wave, such as small pipe breaks or mechanical failures, may not be fully repaired before the next wave arrives. The system as a whole becomes more brittle. You might have lived through a cold snap where you tell yourself that if you can just get through a few nights, things will feel normal again. In a reloading vortex pattern, that promise keeps being postponed.
Pipes that thaw a little during a brief daytime warm-up can refreeze and burst when the next surge arrives. Roads that barely had time to clear of packed snow refreeze. Emergency shelters that were set up as temporary spaces may need to remain open for weeks. The emotional fatigue grows along with the physical strain. There is also a subtler aspect to this. Many of the regions that feel the brunt of these reloading cold waves are not the ones we usually associate with the most extreme winter conditions. They can include parts of the central and southern United States that sit on the boundary between typical Arctic influence and milder climates.
When a vortex lobe dips more deeply into those latitudes, it can deliver anomalies that rival or exceed what people farther north experience in their own context. The shock comes not only from the temperature itself, but from the fact that it invades a place that had shaped its identity around gentler winters. At the same time, the atmosphere does not operate in separate layers with no communication. The same distorted pattern that sends a lobe of the vortex over North America influences storm tracks, jet stream tilt, and the placement of high and low pressure systems around the hemisphere. While one region freezes, another may bask in unusual warmth. While one side of the ocean experiences relentless storms, the other can sit under ridging that deflects moisture away. These contrasts are part of the same large-scale rearrangement of energy. For our story, the key is how that rearrangement sets the stage over North America. A fractured vortex and persistent cold pools to the north create a reliable source of dense, heavy air ready to slide down the continent. That air is so cold and thick that it tends to hug the ground and push outward like a shallow spill of water. When it encounters terrain, it can pile up on one side of mountain ranges, forming cold domes that cling stubbornly to valleys and foothills, even as warmer air glides overhead. This is the bridge between what happens high above us and what happens on the road outside your home. The same dynamics that stretched and split the polar vortex now help build shallow wedges of frigid air along the eastern slopes of the Rockies and the Appalachian Mountains. Those wedges are not just curiosities on a weather map. They are the cold foundations on which the most dangerous kinds of winter storms are built, the ones where ice, not snow, becomes the main weapon. When you hear a forecaster talk about cold air damming, or a stubborn low-level cold pool east of a mountain range, you can now trace that story upward. You can picture the cold originating in a fractured polar vortex, intensifying over snowfields under clear skies, and then being funneled and trapped by the shape of the land. The numbers on the map might simply show a few degrees below freezing at the surface, but those numbers are the visible tip of a much deeper structure. Vintage cold in this context is not only about nostalgia for winters of the past, it is about a specific alignment of factors that allows extreme air to be produced, stored, and repeatedly deployed over the same regions. A stretched polar vortex, regenerating cold pools, snow-covered source regions, and terrain that traps dense air all conspire to create a winter pattern that feels like a test. The question is no longer whether one night will be cold, but how many times the system can reload before something important gives way. That brings us back to the simple but unsettling idea we started with.
The atmosphere is not just delivering a one-time shot of cold. It is shifting into a mode where deep cold becomes a recurring feature for long enough to strain everything it touches. On its own, that is a serious challenge. But the real story unfolds when this entrenched cold interacts with the warm, wet air we explored earlier and with the specific geography of the continent. When that happens, the numbers on the thermometer turn into ice on trees, on roads, and on power lines, and the abstract dance of the vortex becomes something you can feel with every step. When that happens, the winter hazard stops being abstract. It is no longer about distant charts or nameless air masses.
It becomes about whether you can walk across your own driveway, or whether the lights stay on through the night. Snow can make that difficult, but ice turns it into something else entirely. In harsh winters, ice is often the real kill mechanism. Most of us have an intuitive picture of a snowstorm. Snowflakes fall, pile up, and transform the landscape into something soft and muffled. Travel becomes difficult, but the hazard is visible. You can see the drifts, you can judge depth. Machinery can push snow aside and carve a path. In many northern cities, this choreography is almost routine. Crews know how to plough, where to pile, and how to keep main arteries open even when side streets are buried. Ice does not announce itself in the same way. Freezing rain falls as liquid and coats everything in a clear glaze. There are no soft edges, no fluffy mounds that show you where the danger is deepest. A sidewalk can look almost dry, but hold a film that turns every step into a test of balance. A road that seemed passable a few minutes ago can become a place where even slow, careful driving turns into uncontrolled sliding. The hazard lives in the thin interface between rubber and asphalt, between shoe and pavement. From the perspective of infrastructure, that thin layer is monstrous. Snow adds weight, but much of it can be shaken off or physically removed. Ice fuses to surfaces. It adheres to every wire, every branch, every exposed bolt. When rain freezes on contact with power lines, it does not form a light dusting, it builds a heavy, uniform coat. Each additional millimetre adds more load along the entire span between poles. Trees respond in the same way. Branches that have swayed through decades of wind and snow suddenly carry a rigid shell that drags them down. We do not need precise numbers to imagine what that means. Picture a neighbourhood where every tree, every cable, every street sign is carrying a new layer of dense, solid water. That load does not distribute neatly. A limb that was already stressed by age or disease sags first. A pole with minor rot at its base yields sooner. As the night goes on, small failures propagate. A single branch snaps and falls across a line, which sags, which overstrains a distant support that was holding everything in delicate balance.
When people talk about cascading grid failures, this is how they begin. A power system is designed with some redundancy. It can lose a line here, a transformer there, and reroute electricity along other paths. But redundancy has limits. In a major ice storm, damage can accumulate faster than operators can respond. Automatic protections that are meant to save equipment from overload can trigger in quick sequence. One line goes down, then another, and suddenly entire sections of the grid are dark. In that moment, cold becomes something else. As long as your home has power, even intense winter air can be managed with insulation and heating. When the lights go out, the heat loss begins immediately.
Buildings shed warmth faster when the outside air is unusually frigid, and when wind rides along with that chill, the rate of loss climbs further. Elderly people, infants, and anyone with health conditions feel that change sooner. Without electricity, electric heaters and furnaces that depend on blowers fall silent. Even some gas systems rely on electric ignition and fans. One of the cruelties of freezing rain is that it often strikes in temperatures that do not look terrifying on a screen. You might see a reading of just below freezing and assume that exposure is manageable. That is true for bare skin over short periods. It is not true for a house that lacks heat for many hours, or for a person stuck in a stranded car on an impassable road. What looks moderate in a forecast becomes severe when you cannot change your environment, when every escape route is sealed under a crust of glass. Transportation networks are especially vulnerable to this kind of event. Even regions that own fleets of ploughs and salt trucks can be overwhelmed if rain transitions to ice in the wrong way. Salt works best when the road surface has enough residual warmth to help melt the ice, and when crews can treat areas before the worst arrives. In a reloading storm pattern, waves of freezing rain can wash away treatments and refreeze them into uneven, treacherous surfaces. Bridges and overpasses, exposed on all sides to cold air, often glaze first, catching drivers off guard. Imagine being an emergency responder in that setting. Calls come in about downed lines, stranded vehicles, and medical emergencies in homes that have lost heat. Every route you might take is itself a hazard. Even heavy vehicles with chains and experienced drivers are pushing their luck on slopes that have become nearly frictionless. Response times stretch. Decisions that would be simple in clear weather become calculations that balance the risk of delay against the risk of adding another wreck to the chaos. Hospitals and critical facilities carry backup generators for exactly these moments, but those backups are not infinite. They rely on stored fuel, on delivery routes remaining open, on cooling systems that can vent heat properly while the outside world is freezing. In a storm that passes quickly, these backups can ride out the brief gap. In a pattern where ice returns again and again over days, the stress compounds. Fuel trucks struggle to reach their destinations. Maintenance crews work in bitter cold under dangerous conditions to keep systems running. The human stories inside those numbers are intense. Families huddle in the one room of a house where a fireplace still works. Neighbours share blankets, food, and battery-powered lights. People charge phones in cars and carefully run engines in short bursts, trying to balance warmth with the danger of exhaust build-up. Communities set up warming centres, which then become islands that must themselves be supplied and staffed, while the rest of the grid is fragile. All of this would be difficult enough in a region that builds for ice. In reality, some of the worst impacts often strike places that do not see events like this often. In parts of the southern and eastern United States, many power lines still run above ground through tree-lined neighbourhoods. Structures may not be designed for prolonged freezes. Residents may lack snow tyres, chains, or even basic winter gear updated for modern extremes. When an ice storm hits these areas, the gap between design and reality widens quickly. It is not that people in these regions are careless or unprepared in general. They have built their lives around a different set of threats. They know how to handle heat waves, thunderstorms, and heavy rain. They know which creeks flood and which roads wash out. But when Arctic air surges farther south than usual and meets an atmospheric river above, it creates a hazard their systems were not optimised for. The same quarter-inch of ice that would be a serious but manageable event in a northern city can become an existential challenge if it strikes a place that has never had to harden itself against repeated icing. There is a psychological dimension to this. When you wake up to a foot of snow, you see the problem immediately. When you wake up to what looks like wet pavement and grey trees, you might underestimate the danger until you are already in it. People slip on front steps, slide through intersections, and discover too late that their vehicles cannot stop. Each small incident ripples outward. A minor crash blocks an essential route. A downed tree cuts off an entire cul-de-sac. Citizens who might have chosen to stay home if they had seen heavy snow instead venture out. Communication becomes crucial in these moments. Forecasters and officials need to convey not just that frozen precipitation is possible, but that ice, not snow, may be the main outcome. They need to emphasise that travel could become nearly impossible, even if total accumulation looks modest on paper. Yet doing this without inducing panic, and while uncertainty remains about the exact placement of the freezing line, is not easy. You can feel that tension in their language, the struggle to be clear without being alarmist. This is where understanding the underlying pattern helps. When you know that the cold air at the surface is part of a larger, stubborn dome, and that moisture is likely to ride over it in multiple waves, you can treat even a small forecast of freezing rain seriously. You can recognise that a few hours of icing may not be the end of the story, but the beginning of a series of events. Instead of focusing only on the first storm, you can plan for what it would mean if power restoration had to take place under the threat of another. The phrase systemic atmospheric collapse sounds dramatic, But what it really captures is this slow fracture of multiple interconnected systems. It is the way the power grid, transportation network, emergency services, and even individual households are all tested at once by a pattern that refuses to relax. It is not that the air itself has collapsed as a physical substance. It is that the atmosphere has shifted into a mode where the stresses it imposes exceed what the rest of our systems were designed to handle, especially when those systems are already aging or lightly maintained. Think about how quickly a single point of failure can propagate in such a setting. A substation that loses power cascades its outage across entire neighbourhoods. A main road that becomes an impassable sheet of ice forces all traffic into smaller side routes that are no better prepared. A communications tower that ices over and fails can isolate communities right when clear information is most needed. Each failure makes it harder to prevent the next, and the storm above keeps feeding the process. Yet even in the middle of this, there are patterns we can learn from. Past ice storms have shown which kinds of infrastructure designs fare better, which tree species near lines are most likely to cause damage, which emergency protocols succeed in keeping vulnerable people safe when the grid goes dark. Some regions that were devastated once have responded by burying critical lines, reinforcing poles, or changing how vegetation is managed. Others have not yet made those investments because the last disaster feels distant, or because budgets are constrained. If the atmosphere is truly shifting toward more frequent reloading patterns, the cost of inaction will not stay hidden for long. A town that barely coped with one severe ice event a decade ago might now face 2 or 3 in a short span. Repairs that were good enough for a rare event might not hold up under repeated strain. The margin for improvisation shrinks as the intervals between hits shorten. What once seemed like overbuilding begins to look like basic prudence. As we follow this thread from invisible droplets aloft to very visible damage on the ground, a larger geographic pattern begins to emerge. Certain regions will find themselves at the crosshairs more often, not because of bad luck in a single year, but because of how their position on the continent interacts with terrain and atmospheric currents. Among these, there is one zone that keeps showing up in case studies of severe freezing rain, grid failure, and prolonged disruption. A place where cold air loves to pool and warm moisture loves to climb over it. If you trace the map from the interior north down toward the southeastern states, you will notice a long spine of mountains that shapes both wind and temperature. On the eastern side of that spine, the land descends into broad piedmonts and coastal plains where millions of people live. When dense Arctic air spills south and presses against those slopes, it can become trapped, forming a shallow but tenacious wedge of cold that refuses to budge even as milder air flows overhead. The question then becomes simple and unsettling. What happens when that trapped dome of cold meets a reloading river of moisture again and again? When that happens, the Appalachian region becomes a climate trap. Dense Arctic air spills southward and pushes up against the eastern slopes of the mountains, then stops. It cannot easily climb over the high ridges, and it is too heavy to slide back uphill into the interior, so it pools along the foothills and Piedmont, a shallow lake of cold air pressed up against stone. Meteorologists call this cold air damming, and the name is literal. The mountains behave like a dam in a river valley, blocking the flow of dense cold air and letting it pile up on the upstream side. On weather maps, it shows up as a wedge of lower temperature hugging the terrain, often oriented from northeast to southwest. From the ground, you experience it as a stubborn chill that lingers near the surface, even when forecasts hint at warmer air arriving. Above that low-level wedge, the atmosphere keeps moving. Southwest winds at a few thousand feet up transport milder air from the Gulf and subtropical Atlantic. Storm systems track along the frontal zone, pulling in moist flow that glides over the cold dome like water flowing over a submerged sandbar. The result is a vertical structure that is perfectly tuned for trouble. Freezing air near the ground, warm moist air above, and a storm track that repeatedly sends new waves across the same trapped pool. You can see how this plays out in real events. A forecast might call for a wintry mix, changing to rain as warmer air arrives. People in the Piedmont hear that and prepare for a messy morning and a soggy afternoon. But the wedge of cold air near the surface is thicker and more resilient than models predicted. The warm air gliding above cannot fully scour it out. Instead of a quick changeover, freezing rain lingers through the day. The geography of the region reinforces this persistence. Valleys and basins east of the mountains act like pockets where the cold air can settle and deepen. Urban areas like Atlanta, Charlotte or Raleigh sit in positions where they can be brushed by Arctic air from the interior and moist air from the Gulf or Atlantic in the same day. High pressure centered to the north wedges the cold air southward along the slopes, driving it into places that, in a typical winter, might only see rain. If you could stand high above the Appalachians and watch this in slow motion, you would see dense air sliding southwestward along the eastern side of the ridge, hugging the ground and following the contours of the land. You would see clouds thickening as warm, moist flow rides over that shallow, cold river. You would see precipitation begin as snowflakes aloft, melt as they fall into the warm layer, then refreeze on contact with the ground locked in sub-freezing air. The entire setup is a delicately balanced machine, but once it starts, it can be remarkably stable. History offers sobering examples. Past ice storms in the Carolinas, Virginia and northern Georgia followed this script. Forecasts called for mixed precipitation and some icing. Reality delivered long hours of freezing rain that snapped trees, brought down miles of power lines, and left millions without electricity. In some neighbourhoods, the sound of branches breaking under the weight of glaze punctuated the night like distant gunfire. The next morning, entire streets lay under a canopy of shattered wood and sagging wires. One of the reasons these storms catch people by surprise is that the cold air dam is often shallow. A weather balloon launched from a nearby site may show warmer air at just a few hundred metres above the surface. Aircraft reports can confirm that temperatures are above freezing not far overhead.
To anyone looking at those data, the natural assumption is that the warm air will mix down quickly and erode the cold layer. But if the wedge is reinforced from the north and anchored by the mountains, that erosion can stall. Numerical models struggle with this subtlety. Their grids divide the atmosphere into blocks of space and time, and processes within each block are averaged. When cold air is trapped in a thin layer along rugged terrain, its true depth and strength can be underestimated. The model might show surface temperatures creeping above freezing while, in reality, the thermometer on your porch stays stubbornly on the wrong side of that line. That gap between model smoothing and lived experience is where many of the worst surprises lurk.
For residents, the wedge is not an abstract concept. It is the reason a forecast of light icing can turn into a night where the entire neighbourhood goes dark. It is why bridges and overpasses east of the mountains become ice rinks, even as distant highways see only wet pavement. It is why schools close based on the advice of meteorologists who are staring at subtle hints that the shallow cold will not budge, even when the sun tries to poke through thin clouds. Imagine a town near the foothills that has already endured one wave of freezing rain under this setup. Trees are wounded but still standing. Lines have been repaired but not yet hardened. People are exhausted from days without reliable power. Then forecasters notice that the wedge is building back in. Cold air from the north is pushing southward again, pressing against the same slopes. The atmospheric river we talked about earlier is still in place, ready to send another storm along the same track. In that situation, the Appalachians act as both shield and trap. They block some of the worst winds and snowfall that might batter higher terrain, but they also hold the cold in place where most people live. The cities and suburbs in the Piedmont lie in the spillway of the dammed air. When new moisture arrives, it does not have to work hard to find a freezing surface. It simply falls, spreads, and locks in another layer of ice. From space, satellite images after such storms can show an eerie pattern.
Higher ridges may appear white from snow, while the lowlands gleam in a dull grey that indicates ice-coated forests and fields. The transition line between rain and freezing rain can be incredibly sharp, sometimes running along a single interstate corridor or a river valley. On one side, daily life resumes under cold rain. On the other, branches glitter and sag, and the faint buzz of generators replaces the usual hum of the grid. This geography also complicates emergency planning. States that span both coastal plains and mountain foothills must prepare for very different impacts within a few hours of driving distance. Coastal cities may worry more about storm surge, heavy rain, and high wind. Piedmont communities must brace for the quiet, crushing weight of ice.
A single forecast package has to speak to both, and timing matters. If messages underestimate the persistence of the wedge, critical decisions can be delayed. Cold air damming events have another trait that makes them dangerous. They can prolong freezing temperatures near the surface, even after the main storm centre has moved away. The high pressure to the north continues to funnel cold air along the mountains, reinforcing the wedge. Clear skies may appear overhead, but that is often a sign that the dome of cold is firmly in place. The melting, refreezing cycle on roads and sidewalks continues. Black ice lingers overnight and into the morning commute. For people living through this, the lived timeline feels nothing like a simple storm that arrives, peaks, and departs. It feels more like a siege. The first wave ices everything. The second wave arrives before the first layer has fully melted. The third wave may be weaker, but it falls onto an already fragile landscape. Crews who have been working around the clock face another round of outages. Supplies of salt, fuel, and replacement parts are stretched thin. Now connect this local trap to the larger continental pattern, the same distorted jet stream and fractured polar vortex that send Arctic air south also determine where high-pressure systems park. When a strong high settles over the northeastern states or eastern Canada, it becomes the engine that drives the wedge. Its clockwise flow pours cold air down the front range of the Appalachians, feeding the dam day after day.
As long as that high holds, the wedge remains primed. At the same time, the jet stream may be steering a parade of low-pressure systems across the central part of the country, each one tapping the atmospheric river for moisture. The track of those lows relative to the mountains dictates who gets snow, who gets rain, and who gets ice. If the centre passes to the west of a Piedmont city, it is more likely to draw warm air over the cold dome and create freezing rain. If it passes to the east, the cold might win out and yield more snow. Small shifts in these tracks become big differences in impact. This is why forecasters sometimes seem obsessed with the exact path of a storm that is still days away.
They know that a deviation of only a few dozen miles can spell the difference between a memorable nuisance and a crippling ice event east of the mountains. They also know that models can oscillate between solutions as they digest new data. Communicating that uncertainty without losing public trust is a delicate balance. For residents in the crosshairs, one of the most practical signals is not the specific model run, but the persistence of certain phrases. When you repeatedly hear references to cold air damming, cold wedges, or a stubborn low-level cold pool in forecast discussions, that is a hint that the Appalachian trap is in play.
When that language combines with talk of a strong moisture plume, you can infer that the risk of prolonged icing is not just a one-off possibility, but a core concern. Over time, patterns like these leave a kind of memory in communities. People remember the year branches snapped for hours. They recall how long the power was out, which grocery stores had generators, which gas stations stayed open, and which routes were impassable. That memory shapes future reactions. Some invest in backup heat sources or small generators. Others change how they plant trees near lines. Municipalities adjust their emergency plans, sometimes quietly, based on where the worst damage occurred last time. Yet memory can also fade, especially if several winters pass without a major event. Budgets are reallocated.
Maintenance might be deferred. New residents move into neighbourhoods with no personal memory of the last big ice storm. When a reloading pattern finally returns, it finds a mixture of hardened systems and fresh vulnerabilities. The atmosphere does not care which is which. It simply delivers the same physics onto a changed landscape. The unsettling possibility emerging from recent patterns is that events once considered rare in the Appalachian and southeastern region may become more frequent. If the jet stream spends more time in configurations that favour cold air damming and repeated moisture feeds, the interval between major ice storms could shrink. Each event would no longer be an isolated historical marker, but part of a cluster, testing whether prior lessons were fully applied or only half remembered. And what feeds that increased frequency is not only the shape of the mountains or the randomness of individual storms, it is also the behaviour of the cold pools to the north and the broader steering currents at high altitude. If those cold reservoirs are regenerating faster, and if the jet stream is more prone to getting stuck in deep trough and ridge patterns, then the Appalachian wedge becomes a recurring target rather than an occasional victim. To understand that shift, we have to look again at the larger canvas over Canada and the Arctic, where the atmosphere appears to be learning a new habit of reloading rather than relaxing. To understand that shift, we have to look again at the larger canvas over Canada and the Arctic, where the atmosphere appears to be learning a new habit of reloading rather than relaxing. Picture the northern interior of the continent in deep winter. Snow blankets vast stretches of forest and prairie. The nights are long, the sun sits low, and clear skies under high pressure allow heat to radiate away into space. The result is not just cold weather, it is the manufacture of extreme cold air masses that wait quietly for a chance to move. Meteorologists sometimes call these air masses cold pools, and the name fits. They form in basins and broad interior plains where the ground can cool efficiently under snow cover. Each calm night allows the near-surface air to drain a little more heat.
Temperatures drop to levels that many people farther south rarely see on a thermometer. -20, -30, even -40 degrees Fahrenheit are not abstract numbers there. They are the everyday language of midwinter over snow-covered, wind-sheltered land. Once a cold pool is established, it behaves like a heavy liquid. It hugs the ground, flowing slowly outward from its source areas whenever pressure patterns and terrain permit. High-pressure systems at the surface act like lids on these pools. They keep skies clear, winds light, and the cooling process going night after night. Instead of dissipating, the cold deepens. It is as if the freezer in the back room is not only stocked but set to an even lower temperature every evening.
Now place this freezer beneath a distorted jet stream. Far above, strong ridges of high pressure over the Pacific or over Greenland can lock the pattern into place. Between those ridges, a deep trough digs south over central North America. The jet stream winds wrap around that trough, guiding storm systems and helping to lift Arctic air out of its source regions. The cold pools that formed quietly over Canada suddenly have an open door southward. When a strong front develops along the edge of that trough, it becomes the leading edge of the cold pool. To people on the ground, it arrives as a distinct line where wind shifts and temperatures crash. In some events, readings can fall by 20 or 30 degrees over a few hours as the dense air surges in.
Behind the front, the sky may clear and the landscape may grow calm. It can feel like the event is over. In reality, that is when the deeper reloading process begins. The first surge of Arctic air spreads across the central states, reaching as far south as the Gulf Coast or the subtropical deserts. At the same time, the source region in Canada begins to refill. Snow remains on the ground. Night is still long. Another surface high-pressure system settles in and starts the radiative cooling cycle again. Within a few days, temperatures in that region can drop back to levels as extreme as before, or even lower, despite the fact that a large volume of cold air was just exported. This is the detail that makes meteorologists uneasy. The recovery time for the cold pool is short. The jet stream pattern overhead has not changed much. The trough is still anchored in roughly the same place, sandwiched between stubborn ridges. That means the atmosphere is ready to send another strong front south, before people and infrastructure in the path have fully recovered from the last one. The freezer keeps refilling faster than the kitchen warms back up. From a distance, maps of such periods can show a repeating heartbeat. Each surge of Arctic air pushes anomalies far below normal, across a wide swath of the continent. Then, for a brief interval, temperatures moderate slightly as the edge of the cold shifts, or as milder air noses in a loft. Before the system can relax into the old baseline, another pulse arrives.
The absolute numbers may vary from day to day, but the underlying regime stays locked on cold. In this kind of pattern, individual storms are like waves on top of a rising tide. You might remember one specific blizzard, one night of freezing rain, one day when the wind chill made your lungs ache. But the deeper story is the persistence of a background state that favours extremes. Heating systems that could handle one intense event begin to strain under weeks of near constant demand. Power grids built for peaks of a few days face peaks that blur into each other. As the pattern drags on, cold fronts can begin to interact and merge in ways that amplify their punch. A fresh lobe of Arctic air may surge south and collide with the remnants of a previous front stalled farther down the continent. Their boundaries confuse, creating a sharpened dividing line between air masses. To someone looking at a satellite or radar loop, the resulting feature might resemble a supercharged front, a superblast of cold barreling into regions that had just begun to thaw. For people living in those regions, the word siege becomes more accurate than storm. Day after day, high temperatures fail to reach values that normally feel comfortable in that season. Night after night, pipes sit near their failure point. Small weaknesses in buildings and infrastructure that might survive a brief cold snap are pushed again and again. A tiny crack in a water main widens with each freeze and partial thaw. A worn component in a substation warms under high load and then is shocked by the next plunge. Energy systems face some of the harshest tests. Natural gas demand for heating spikes as electric demand climbs for heat pumps, space heaters, and industrial processes. Power plants designed with certain temperature assumptions in mind may struggle in extreme cold. Components can become brittle, fuel lines can gel. Cooling systems that rely on outside air may not respond well when that air is far colder than design specs ever imagined. During a single short event, operators can often juggle these constraints. During a prolonged regime, juggling turns into a desperate balancing act. You might remember images from past winters where fountains froze in southern cities or where icicles hung from ceiling fans in homes with burst pipes. Those scenes were not produced by some sudden alien climate. They were the visible outcome of reloading cold pools and a stuck jet stream, directing them over regions unaccustomed to such extremes. Each new episode of this pattern adds layers to the collective memory and to the debate over whether something deeper has changed. In that debate, a kind of mistrust can spread almost as quickly as the weather itself. People see repeated Arctic blasts hitting certain areas and begin to wonder whether there is more at work than natural patterns. Social media posts frame the events as evidence of hidden control, deliberate experiments, or secret technologies gone wrong. The language of systemic atmospheric collapse gets folded into narratives that blame unseen hands, rather than the messy physics of a spinning planet and a warming climate. Part of this mistrust comes from the way information reaches us now. Forecast model graphics are shared widely, often without context. One run that shows extreme cold in a week is posted, then a new run shows a shift, and the original map continues to circulate long after it is outdated. To someone not steeped in the daily grind of meteorology, it can look like forecasters are constantly changing their minds, while the real story is being concealed. In reality, the uncertainty around details does not mean the big picture is fake. It means the atmosphere is in a volatile state, where small initial differences cascade into different local outcomes, even while the overall regime of reloading cold remains. The models are arguing about exactly where and when, not about whether the cold pool exists or whether the jet stream is stuck. When you step back from the noise of individual frames, the persistence of the pattern is hard to miss. Forecasters find themselves in a difficult position. If they emphasize the potential severity too early, they risk being accused of hype if small shifts reduce impacts in some places. If they hold back, they risk leaving communities underprepared when the worst case does materialize. In a reloading pattern, this tension is amplified. They are not warning about a single, discrete disaster. They are trying to explain a mode of the atmosphere that can deliver multiple blows, each shaped by subtle variations on the same theme. Meanwhile, the physics behind that mode are entirely capable of producing what we see without any help from human manipulation of the weather. A jet stream locked between strong ridges, cold pools regenerating quickly over snow-covered terrain, and a sequence of fronts that tap those pools in different ways are all natural features of a chaotic fluid system. Human-driven climate change layers additional energy and moisture onto that system, influencing the odds of certain extremes, but it does not require hidden buttons in a control room to send a series of Arctic blasts into the mid-latitudes. That does not make the pattern any less frightening when you are living through it. In some ways, it makes it more unsettling. A controllable system can be fixed by changing settings. A semi-chaotic system responding to broad forcings cannot be tuned so easily. The same background warming that increases heat waves in summer can also alter snow cover, sea ice, and pressure patterns in ways that influence winter extremes. Scientists are still debating the exact links, but they agree on one thing. The climate our infrastructure was built for is not the climate it will face in the coming decades. In a reloading winter, you can see the mismatch exposed in real time. Roads designed for occasional frost heave crack under repeated cycles. Water systems that were never insulated for deep cold fail. Power lines strung in open-air fields gallop and ice over. Even communication networks can buckle as towers glaze and as backup systems run longer than their designers intended. Each weakness reveals a place where yesterday's assumptions are colliding with today's atmosphere. Yet there is another layer to this story that goes beyond infrastructure. Patterns like these also act as stress tests for our social systems and for our ability to trust information. As more people have access to raw data and model output, the gap between expert interpretation and public perception widens. Some use the data to learn and prepare. Others cherry-pick the most alarming images to feed fear or anger.
In the noise, it can become harder to hear the measured voices trying to explain what is actually going on. All of this is happening while the tools we use to predict the atmosphere are themselves changing. Traditional models based on physics are being joined by artificial intelligence systems trained on vast archives of past weather. These new tools can sometimes predict the broad shape of patterns like reloading cold pools and stuck jets with surprising skill. But they can also be opaque, offering a forecast without a clear explanation of the underlying mechanics. For a public already skeptical about complex systems, black box forecasts can either deepen distrust or encourage overconfidence, depending on how they are presented.
In the end, the image that remains is simple, even if the science behind it is not. Over Canada and the Arctic, extreme cold keeps forming over and over on snow-covered ground. High above, the jet stream bends and stalls, directing that cold southward in repeated waves instead of letting it disperse. Each wave collides with moisture in different ways, producing snow here, ice there, and prolonged chill across wide regions. Between waves, the atmosphere does not fully reset, it reloads. The question that hangs over all of this is whether we are looking at a temporary quirk of natural variability, or at a sign that the larger climate engine is shifting into a new gear. To answer that, we have to widen our field of view even more. We have to look at how storms over distant oceans are linked to these patterns, how sudden warmings high in the stratosphere ripple downward, how the sun itself and our growing dependence on complex technology interact with a more turbulent atmosphere. When we widen that field of view, we start to see that the atmosphere over your head is entangled with events unfolding half a world away. Storms in the Western Pacific, bursts of tropical thunderclouds rising near the equator, and pulses of warmth high over the Arctic are all tugging on the same invisible threads. Those threads are what meteorologists call teleconnections, long-distance links in the fluid system that can turn a storm over one ocean into a cold wave on another continent weeks later.
One of the strongest of these links runs through the tropical Pacific. When waters there warm or cool over large areas, the pattern of rising air and thunderstorm clusters shifts. That shift pushes on the high-altitude winds that circle the globe. During certain phases, storm tracks are nudged poleward, and the jet stream strengthens. In others, it buckles and wobbles, sending deeper troughs into the mid-latitudes. The Arctic air that feeds our reloading cold pools is not immune to these nudges. It responds like a pendulum being tapped from far away. Closer in time, the atmosphere features shorter rhythm patterns, like the Madden-Julian oscillation. This is a pulse of enhanced storminess that travels slowly around the equator.
When it passes over certain longitudes, it can spur stronger or weaker jet streams downstream. A burst of convection over the Indian Ocean weeks earlier can prime the flow that later carves a deep trough over North America. To someone watching from the ground, a cold wave may feel like a sudden ambush. To the atmosphere, it is a scheduled consequence of many previous moves. Then there is the realm above the jet stream, where sudden stratospheric warmings take place. We met them earlier as the events that can stretch and shred the polar vortex. What drives them often begins down in the troposphere, where mountains, land-sea contrasts, and storm tracks generate waves in the airflow. Those waves carry energy upward, like ripples in a pond that climb instead of spread outward.
When enough energy accumulates in the stratosphere, temperatures can spike dramatically. Winds change direction. The polar vortex falters. When a major warming unfolds, it sends signals downward as well. Over days and weeks, the altered flow in the stratosphere can reach into the levels where everyday weather systems live. High-pressure ridges may strengthen in some locations and weaken in others. Jet stream paths adjust. In some cases, this helps lock in the same kind of stuck patterns we have been talking about, with deep troughs over one continent and stubborn ridges over the oceans. The connection is not instant, but it is real enough that forecasters now watch the stratosphere closely as a harbinger of surface extremes. All of this can feel like an elaborate chain reaction. A storm over the Pacific changes the pattern of rising air. That change feeds waves into the stratosphere. A sudden warming scrambles the vortex. Weeks later, a lobe of cold air descends over North America. At the same time, tropical convection pulses again, helping to steer atmospheric rivers that tap into the moisture of distant seas. The pattern that delivers ice to your street lamp is not born from a single cause. It is the final act of a long, complex play. On top of these atmospheric connections, there is another influence that people have watched with equal parts fascination and dread for centuries. That influence is the sun. Our star bathes Earth in energy, both as light and as streams of charged particles.
Its magnetic field flips and fluctuates over cycles of roughly 11 years. During active phases, dark sunspots dot its surface, and eruptions hurl billions of tons of plasma into space. When those eruptions intersect Earth's magnetic field, they can trigger geomagnetic storms. To most of us, the first sign of such a storm is the aurora, curtains of coloured light shimmering at high latitudes and occasionally dipping into lower ones. But for the infrastructure that keeps modern society running, geomagnetic storms have a sharper edge. When charged particles from the sun buffet Earth's field, they can induce electric currents in long conductors. High-voltage transmission lines, pipelines, and even undersea cables can feel that induced current. Transformers in power grids are particularly vulnerable if the storm is strong and long-lasting. Imagine facing a reloading winter pattern with its repeated ice storms and cold waves, while at the same time the sun enters an active period in its cycle. The same grid that is stressed by heavy demand for heat, by ice loading on lines, and by mechanical strain in substations is also exposed to surges from space weather. Operators must watch not only the forecast models for temperature and precipitation, but also alerts about solar eruptions millions of kilometers away. There have been real events where geomagnetic storms damaged transformers and caused large-scale power outages. In milder cases, protective systems shut down parts of the grid to prevent damage, creating temporary blackouts. In more severe storms, physical equipment can be permanently harmed, requiring replacement units that are not easy to source quickly. When you lay that risk on top of a winter regime that already stretches repair crews and supplies, you start to see why solar activity enters the conversation about systemic stress. To be clear, the sun does not cause every winter cold wave, nor does every geomagnetic storm lead to disaster. Most are managed quietly by engineers who have trained for decades for such events. Yet there is an uncomfortable overlap when solar peaks and atmospheric extremes coincide. A single failure in timing and coordination can cascade through systems that rely on each other. The question is not whether nature is out to get us,
It is whether we have built enough buffers into our networks to handle overlapping stressors. As we wrestle with these layered risks, the tools we use to understand the atmosphere are undergoing their own transformation. For most of the modern era, weather forecasting has rested on a straightforward idea. If we can measure the state of the atmosphere now, and then apply the laws of physics through powerful computers, we can project how that state will evolve. The models built on this idea are called numerical weather prediction models. They solve equations of motion, thermodynamics, and moisture step by step on a grid. These traditional models have grown steadily more accurate as computing power and observations improved.
They can capture broad patterns days in advance and local details a day or two out. Yet they still have blind spots. Small-scale processes like the exact depth of a cold wedge or the intensity of an atmospheric river are challenging to resolve. Errors in initial conditions, such as temperature and moisture in remote regions with few observations, can grow quickly. The result is the familiar spread in model outcomes that forecasters must interpret. Recently, a new class of forecast tools has joined the scene. These are machine learning models trained on decades of past weather data. They do not solve the equations in the same explicit way. Instead, they learn patterns from the archive, finding statistical relationships between current states and future ones. When fed today's observations, they generate a forecast based on what most resembles similar situations in the past. In some tests, these systems have matched or even outperformed traditional models at certain lead times. On paper, that sounds like a breakthrough. If an artificial intelligence system can look at the entire history of weather and recognize subtle combinations of signals that hint at reloading cold pools or stuck jet streams, it could provide earlier warnings of regimes like the ones we are discussing. It might notice teleconnection patterns, stratospheric precursors, and tropical convective phases in a way that feels instinctive rather than explicit. It could, in theory, say the atmosphere is about to lock into a siege pattern days before conventional models converge. The challenge is that these systems are often black boxes. They produce outputs without offering a clear chain of reasoning in human language. A meteorologist can inspect the internal fields of a physics-based model and see how a trough deepens or how a jet streak strengthens. They can check whether the model is handling moisture transport or radiative cooling in a reasonable way. With an AI model, the path from input to forecast can be opaque. It just says, "Trust me, I have seen patterns like this before." For many forecasters, that is both exciting and unsettling. They gain a powerful new tool, but they also face a dilemma about how much weight to assign to a system they cannot fully interrogate.
If an AI forecast insists that a deep cold regime will persist for weeks, while traditional models are more cautious, which do you believe? Do you alert the public to a possibility that might be real but is hard to explain? Or do you wait for confirmation from the older tools and risk losing valuable lead time if the AI was right? For the public, the problem is even trickier. Imagine seeing forecast maps from multiple sources, some generated by long-standing national weather agencies, and others by private companies using proprietary machine learning models. They may not agree. Some may show extreme cold or heavy ice days ahead, others a more moderate pattern.
Without context, it is easy to mistake model diversity for deception or incompetence, when in fact it reflects honest uncertainty in a complex system. In a world already full of conspiracy theories about weather control and hidden agendas, the arrival of black box forecasts can feed suspicion. People hear that artificial intelligence is now predicting the weather and jump to the idea that it might also be manipulating it. They see mismatched forecasts and assume someone is hiding the truth. The deeper reality is less cinematic and more challenging. We are layering new, partially opaque tools onto an already complicated science, and we are doing it in front of billions of skeptical, anxious viewers. This does not mean we should abandon these tools.
It means we have to learn how to use them wisely. One approach is to treat AI models as additional ensemble members, not as replacements for physics. Forecasters can compare what the machine suggests with what the traditional models show, and with their own understanding of the pattern. When all three align on a regime of reloading cold and repeated ice threats, confidence grows. When they diverge, caution and clear communication become even more important. Another approach is to focus on what matters most for real-life decisions. Individual model runs may disagree on the exact temperature in your town next Thursday, but they may all agree that the large-scale pattern favours below normal temperatures and multiple storm opportunities. Sharing that consensus early, while acknowledging the local uncertainty, can help people prepare without locking them into a specific brittle expectation. The goal is not to deliver a perfect deterministic forecast. It is to convey the range of plausible outcomes and the reasons behind them. Trust is built when explanations are honest about limits. When forecasters say they do not yet know whether the freezing line will sit north or south of a particular city, but can show why both outcomes are on the table. They invite the public into the investigation instead of talking down to them. When they explain teleconnections, stratospheric influences, and the role of cold pools in plain language, they help people see that extreme patterns are not arbitrary cruelty. They are the atmosphere exploring configurations that are rare but entirely possible. In a reloading winter pattern, this kind of trust can mean the difference between a community that responds cohesively and one that fractures. People who understand that the underlying regime favours repeated stress will be more likely to conserve energy, check on vulnerable neighbours, and pace their resources. People who believe each event is either overblown or part of a hidden plot may swing sharply between apathy and panic. The same physical storm can produce very different social outcomes depending on the story wrapped around it. There is a final layer to this, and it loops back to the larger question hanging over the entire documentary.
Teleconnections, solar cycles, and new forecast tools are all pieces of a bigger puzzle. That puzzle is where the Earth's climate system is entering a new phase, where extremes cluster more tightly, where patterns get stuck more often, and where reloading events become a defining feature rather than an occasional shock. To approach that question, we have to step even farther back, beyond any single winter or region. We have to look at the long-term imbalance in the planet's energy budget, at the way additional heat trapped by greenhouse gases is stored in the oceans and atmosphere. We have to consider how that extra energy can fuel both heavier rain and deeper drought, stronger heat waves and more moisture-laden snowstorms. We have to ask what happens when an already complex fluid engine is given a steady push into a state it has not seen in human history, while our infrastructure and expectations remain tuned to the old settings. And as we ask those questions, another thought lingers at the edge of the frame. Earth is not the only world where atmospheres flip between regimes. Other planets in our solar system have shown sudden, dramatic shifts in storms, winds, and cloud belts. Some have entered long-lived patterns that look almost frozen in place. If we want to know whether our own planet is merely wobbling within natural bounds, or tipping into a new operating mode, it might help to study those other worlds, to see what happens when a climate crosses an invisible threshold and begins to behave in an entirely different way. When we look at that bigger picture, the first thing that stands out is how much extra energy we have added to the planet. Greenhouse gases trap more of the sun's heat, and most of that excess ends up stored in the oceans. Warmer oceans evaporate more water into the air. That means that for every cold front and every storm, there is now a deeper reservoir of moisture waiting to be tapped. At the same time, the background temperature of the atmosphere has nudged upward, changing when and where snow, rain, or ice can form. So we find ourselves in a strange position. We live on a warming world that can still deliver brutal cold snaps and heavier winter storms than many of us remember. On the surface, that feels like a contradiction. People ask how there can be fierce snowstorms, historic freezes, or epic ice events if the planet is warming. The answer lies in the way climate change reshapes patterns, not just averages. Think of a river whose flow has increased. The water level rises, but the way it meanders also changes. New bends form, old channels dry out, and floods visit places that rarely saw them before. In the atmosphere, that added energy changes the amplitude and persistence of waves in the jet stream. Some ridges grow stronger and last longer, some troughs dig deeper. Moisture plumes like atmospheric rivers become richer and more frequent. The dice for both heat and cold extremes are loaded in new ways. In winter, that extra moisture can mean more snow where the air is still cold enough, and more freezing rain where warm layers aloft override shallow cold near the ground. The kind of ice storm that once demanded a rare, perfect alignment of ingredients may now find those ingredients more often. Meanwhile, the presence of more blocking highs and deeper troughs can help lock a pattern into place. Instead of a quick swing between warm and cold, the jet stream can park itself in a configuration that favours reloading cold pools over the same regions again and again. This is where the question emerges about what is just weather and what hints at a deeper phase change in the climate system. Weather is the day-to-day dance of storms and fronts. Climate is the long-term pattern of how often those dances occur and how strong they tend to be. When we see one intense winter event, we can chalk it up to the natural swings of a chaotic atmosphere. When we start to see clusters of extremes, regimes that repeat more often, and patterns that seem more reluctant to break, we are forced to ask whether the underlying stage is shifting. Complex systems often do not change gradually in a neat line. They wobble around a familiar state for a long time, then suddenly jump into a new mode of behaviour. A lake can stay clear and cool for years, then cross a threshold where algae blooms become common and the water chemistry flips. An economy can appear stable until a hidden stress pushes it into a recession that feeds on itself. In physics, these are sometimes called regime shifts. The system as a whole moves from one pattern of organisation to another, and returning to the old pattern becomes difficult, even if the original push is removed. Our atmosphere shows signs of operating in similar ways. Over the course of recorded history, we have seen eras where certain storm tracks dominate, where droughts cluster, or where certain regions experience repeated harsh winters. Many of these episodes were driven by natural cycles in ocean and atmosphere. What makes the current era different is that we have added a persistent, human-caused push on top of those cycles. We are warming the base state of the system and then asking it to behave as if nothing has changed, even as sea ice retreats, snow cover shifts, and the contrast between different regions evolves. If we want to understand what might come next, it helps to look at other worlds that have already demonstrated their own regime changes. Take Jupiter, for example. Its atmosphere is banded with belts and zones, striped features that circle the planet. For decades, those bands looked almost unchanging to casual observers, but detailed monitoring has revealed periods where the colour, width, and intensity of those bands shift dramatically. Zones that were bright can darken. Belts can widen or narrow, sometimes disappearing from view before returning. The famous Great Red Spot, a giant storm large enough to swallow Earth, has itself changed in size and colour over the years. Saturn offers another example. Every few decades, that planet experiences a global-scale storm that wraps around its entire circumference. These so-called Great White Storms erupt from deep within the atmosphere and can alter cloud structures and wind patterns for years afterward. They mark a kind of atmospheric reset, after which the planet settles back into a different arrangement of bands and eddies. Neptune shows dark vortices that appear and vanish. Mars has dust storms that sometimes grow into planet-encircling events, reshaping temperatures and winds until the dust falls again. None of these other worlds has cities, power lines, or fragile infrastructure. Their atmospheres shift regimes with no one there to notice except our orbiters and telescopes. There is comfort in that perspective. It reminds us that dramatic pattern changes are a natural feature of fluid envelopes on spinning planets. There is also a warning hidden in it. Those planets show us that once a system crosses an internal threshold, it can enter modes that last for years or longer, modes that look nothing like what came before. Earth is not Jupiter or Saturn, and our climate has its own rules. But we know that our planet too has experienced regime shifts. During past ice ages, jet streams and storm tracks ran in different places. During abrupt events in ancient climate records, temperatures in some regions changed by many degrees within human lifetimes or less. These shifts were often linked to changes in ocean circulation, ice cover, or greenhouse gases. Today, we are changing those gases ourselves at a speed that rivals or exceeds many natural events in the past. So when we see the jet stream behaving in ways that seem more locked, more amplified, and more prone to reloading extremes, it is reasonable to ask whether we are nudging the system toward another kind of regime. One possible signature of such a shift is the rise of what we might call reloading systems across different parts of the climate engine. We see cold pools in the Arctic and over snow-covered continents that regenerate quickly. We see fire seasons where the fuel dries out faster than landscapes can recover, so each new heatwave or lightning burst can ignite fresh megafires. We see flood patterns where rivers are hit by heavy rainfall events in close succession, leaving little time for watersheds to drain and rebuild their banks. The breaks that used to separate one major event from the next are wearing thin. Our human systems are not immune to this pattern. Power grids, water networks, transport corridors, and information systems were mostly designed for a climate in which extremes were rare outliers. They assumed that after a serious storm or cold wave, there would be enough quiet time to repair, rebuild, and rest. In an age of reloading, that assumption breaks. A region can be hit by a heat wave, then a wildfire, then a flood, or by a winter of repeated ice storms, all within spans that feel uncomfortably short. Each event leaves behind damage that is not quite fixed when the next one arrives. You can see this in the stress that accumulates in communities. Emergency crews operate in near-continuous crisis mode, rather than in occasional surges. Budgets that once reserved funds for rare disasters are drained more often.
Repair work becomes triage instead of long-term strengthening. People who once thought of major storms as once-in-a-generation experiences now recognise the pattern in their own lifetimes. They start to speak of eras by the names of clusters of events, rather than by single dates on the calendar. Overlay all of that with the way information moves now and you get another reloading system, this time made of attention and emotion. Every extreme weather event produces waves of images and commentary online. These waves overlap just as the storms do. Before a community has processed one disaster, it is confronted with the next, somewhere else or right at home. Warnings, conspiracy theories, scientific explanations, and raw fear all mixed together. Trust in institutions flickers in and out like a faulty light, just when we most need clear guidance. So where does that leave us? It would be easy to interpret all of this as confirmation that we are helpless passengers in a failing system. But complexity cuts both ways. The same interconnectedness that makes us vulnerable also gives us leverage. Small changes in design, policy, and behaviour can cascade in the opposite direction, creating resilience that reloads as well. Consider power grids again. A network that relies heavily on a few long transmission lines and centralised plants can fail catastrophically when ice storms or geomagnetic events strike.
A grid that diversifies, with more local generation, smarter controls, and hardened critical nodes, can absorb damage and reroute power more gracefully. It does not eliminate risk, but it shifts the system toward one where recovery time shrinks and where each repair leaves the network stronger rather than merely patched. The same is true for buildings and water systems. Better insulation, smarter valves, and designs that anticipate deeper cold or heavier rain can turn a reloading pattern into a series of manageable challenges instead of devastating shocks. Each upgrade installed after one event becomes a shield for the next. The system learns in hardware. Communities that invest in mutual aid networks, clear communication channels, and protection for their most vulnerable members learn in software and social fabric. For you, as an individual, adaptation does not require solving the polar vortex or the solar cycle. It begins with understanding the patterns well enough to make more grounded choices. If you live in a region that sits near the collision zones we have discussed, you can treat talk of atmospheric rivers and cold wedges not as distant jargon, but as practical signals. You can prepare as if reloading events are not freak accidents but real possibilities. That might mean simple steps like having backup ways to stay warm, store water, or stay informed. It might mean supporting local decisions that harden infrastructure, even when the sky is calm. There is a quiet courage in that kind of preparation. It rejects both denial and doom. It accepts that the atmosphere may be entering a more volatile phase, while refusing to surrender to helplessness. It recognises that, while we cannot control every teleconnection or solar flare, we can control how brittle or flexible our own systems are when those forces play out. Stepping back one last time, there is also something almost poetic in the way this story connects us to the wider cosmos. We live under a thin layer of air on a small rocky world orbiting an ordinary star. That air has flipped modes before, and will do so again long after we are gone.
The difference now is that there is a species within it that can see the pattern changing and can choose how to respond. We can look at Jupiter's shifting bands, Saturn's rare global storms, and Neptune's wandering dark spots and recognise distant cousins of our own atmospheric dramas. That recognition invites a kind of humility. We're not outside the system, controlling it like a thermostat. We're inside it, part of the feedback loops, capable of warming the planet and altering its patterns, but also capable of learning and adapting. The age of reloading systems need not be defined only by cascading failures. It can also be defined by how quickly we absorb lessons, how deliberately we build buffers, and how clearly we see the thin line between normal variability and dangerous change.
The winter patterns we have traced, from ghost years in the past to the reloading cold of the present, are one chapter in that larger story. They remind us that the atmosphere can hold a configuration for weeks that tests everything we have built, and that new technologies and old physics will both shape how we face those tests. They show that what feels like an isolated storm can be the visible face of a global chain of events reaching from tropical seas to the edge of space and even to the sun. The question that remains is not whether these patterns will eventually shift. They always do. The question is whether we will shift with them fast enough, whether we will treat the age of reloading systems as a passing inconvenience or as a clear signal that the rules we built our world around are changing, whether we will let each new extreme harden our divisions or deepen our understanding of just how delicately everything we care about rests on the moving air above our heads. Some future winter will arrive when the jet stream bends in a new way, when cold pools behave differently, when the analogues to 1985 or any other ghost year finally break. When that happens, someone will look back on these years and see them as part of a transition, a time when the atmosphere was already telling us that its habits were changing. What they write about how we listened and how we adapted is the part of this story that is still unwritten and that belongs to us now.